In this question, we want to classify the given function as a polynomial function, a rational function, a root function, and then find the domain. And we want to write our domain in interval notation. So let's first start by classifying. It's a little bit easier to classify rational functions and root functions. They tend to be a little bit more obvious. Rational functions are the functions where we're going to see a variable in the denominator of a fraction. And root functions, those are the ones where you're going to see a radical in the function. So you'll see a radical with some index. Usually everything else is considered to be a polynomial, but there are specific rules for polynomials. Your variables are going to be raised to powers, and those powers need to be whole numbers. So you have to have a nice power, 0, 1, 2, 3, and so on for something to be considered a polynomial function. So looking at this example, we have g of x equals the fourth root of 5 minus x. So we're going to classify this as a root function because it has a radical. We also want to find the domain of this root function. So we need to know about the two different types of root functions. We have roots that have an even index and roots that have an odd index. So the index is this number right here. So in this particular example, our index is 4, and so we have an even index. But I want to talk about how we find the domain in each case. Now, when we have an odd index, the root function has no restrictions on the domain. And having no restrictions means that our domain is going to consist of all real numbers. So if we have an even index, it's a little bit different. I can give you some examples. We do have restrictions with even index. For instance, if we take the square root of -1, this is not a real number. This is the imaginary unit I. So if we take the square root of a negative number, that produces a complex number instead of a real number. And it's also any time we have the even root of a negative number, we get something that is not real. And so root functions with an even index have restricted domains, and you have to have what's underneath the radical being positive or 0. So that is everything that is not negative. So when we're looking for the domain of an even index root function, we're going to take what's underneath the radical and we want to set it greater than or equal to 0. Greater than or equal to 0 is excluding negative numbers, since we have since those are the restricted values. So we're going to solve this inequality by subtracting 5 on both sides. We get negative x is greater than or equal to -5. And we want to continue solving by dividing both sides by a -1. Now, when we divide an inequality by a negative, we have to reverse that inequality symbol. So this becomes x is less than or equal to 5. If we were to think of this on the real number line, we would mark 5 with a filled-in circle and shade everything that is less than 5. In interval notation, that would be -infinity to 5 including the 5, so we would have a bracket. And we could also write this in set builder notation. In set builder notation, we would say x, such that x is less than or equal to 5. And we could state the domain that way. In this example, it's looking for interval notation, which is this one here. Negative infinity to 5, with 5 included. For this question, we want to solve the exponential equation using the method of relating the bases by first writing the equation in the form e to the u equals e to the v. Now this form is very desirable because once we get the equation in this form, we're going to be able to simplify the equation by saying that the exponent on the left is equal to the exponent on the right. So this format, e to the u equals e to the v, will allow us to simplify the equation to u equals v. So we're going to do that with the equation that's given to us. We have e to the x squared to the 5th power equals e to the 180. So first I'm working to get it in this form, which has the base being e on both sides. More importantly, the base is the same on both sides. Now, on the left-hand side, I'm able to use one of the properties of exponents called the power rule, and that allows me to multiply these powers together, and that gives e to the 5x squared equals e to the 180. So now I have the equation written so that the bases are the same on both sides, and I can set the exponents equal to each other. This gives 5x squared equals 180. I want to get x squared by itself, so I'll divide both sides by 5. And x squared equals, let's see, 5 goes into 18 3 times, 3 left over, 5 goes into 36 times. So 180 divided by 5 is 36. I can then square root both sides, and that gives x equals plus and minus 6. So we got two solutions to this exponential equation, positive and negative 6. I want to use the properties of logarithms and the logarithm property of equality to solve the logarithmic equation. So let me state a few of the properties that we're going to use to help us with this question. So I notice that I have a 2 as a coefficient to this log. So that means we're going to use a property that we call the power rule. The power rule for logarithms is when you have, let's say, a p multiplied by log base b of m. So if you have a number that's multiplied on the log, you're allowed to move that coefficient into the exponent. So we could write this as you can write it as log base b of m to the p power. So that's one property we're going to use. And another property we're going to use is adding logs with the same base, and that's called the product rule for logarithms. So this product rule looks something like this. If you have log base b of m plus log base b of n, if you're adding logs that have the same base, you can combine the logs into a single log. I call that condensing. You can condense into a single log with multiplication. That's why it's called the product rule, because you're multiplying the numbers together. So log base b of m plus log base b of n is equal to log base b of m times n. And then finally, it mentions here the property of equality. The property of equality is what we use to simplify our equation. and it looks something like this. We have log base b of m equals log base b of n. So anytime we have logs equal to each other that have the same base, we are able to simplify the equation by saying what's inside the log on the left is equal to what's inside the log on the right. So we're going to use these properties to solve the equation that we have. So our goal is to write the equation like this so that we can simplify it. So in order to write the equation with a single log on the left-hand side and a single log on the right-hand side, I've got to use the power rule to get rid of that 2. So I would write log of x plus 5 squared using that power rule. On the right-hand side, I want to write a single log, so I'm going to condense with the product rule and write this as log of 32 times 2. So this is log of x plus 5 squared equals log of 64. And now that I have a single log on both sides of the equation, I can use that property of equality. So what's inside the log on the left, x plus 5 squared, has to equal what's inside the log on the right, 64. And now I have a simpler equation that I know how to solve. I'm going to solve this by getting rid of the square on both sides, by square rooting it. The square and the square root cancel each other out, leaving me with x plus 5 equals plus or minus. The square root of 64 is 8. Now solve for x by subtracting 5 on both sides. That gives x equals negative 5 plus and minus 8. Negative 5 plus 8 is 3, and negative 5 minus 8 is negative 13. I'm going to check both of these solutions in the original equation because log equations have restricted domains. So I need to make sure that I don't have an extraneous solution. So let's check x equals 3. In the original, that would be 2 times the log of 3 plus 5 equals the log of 32 plus log of 2. So what I'm checking is to make sure that this is a positive number. 3 plus 5 is 8, which is positive. And this log is positive and this log is positive, so we're going to be able to keep the solution of 3. Then we're going to check the other solution, x equals negative 13, and when I substitute that into our log expression, I get negative 13 plus 5. And negative 13 plus 5, when I add those together, gives a negative number. And log of a negative is undefined, so this number can't possibly be a solution because when I substitute it into the equation, it makes the expression undefined. So the only solution to this logarithmic equation is x equals 3. We want to solve the equation ln of 2x plus 1 plus ln of x minus 2 minus 2 ln x equals 0. So in this example, I have a log equation, and I kind of keep in the back of my pocket 2 main methods for solving logarithmic equations. So the 2 methods are to convert or to use this property of equality. So if you keep these 2 methods in the back of your mind, You might know, it might indicate to you which one you're going to use on this example. So if you are going to convert, you're going to have some log equation, y equals log base b of x, and you're going to convert that to an exponential. So that would be b to the y equals x. But when you use the property of equality, you need a log of something equals log of something. And we got to have the log with the same base on both sides to be able to solve it. And what you do is you say what's inside the log on the left is equal to what's inside the log on the right. So when you have these two in your mind, what I'm noticing is that this has log only on one side. Sorry, I meant to highlight there. This has log only on one side, and this has log on both sides. So when I look at this equation, I notice that my log is all on one side. So I might think to use the converting method. So let's take a look at how that comes out. So if I choose to convert, I want to try to get the equation to look something like this, have log only on one side. And I can only have one of them, so I need to condense all of these logs together. So I also need to use the power rule to bring that exponent to, that coefficient to the exponent. And I would have natural log of 2x plus 1 plus natural log of x minus 2 minus natural log of x squared. And then I would condense down to a single log using both the product and the quotient rule for logarithms. So using the product and quotient rule, we would multiply these two logs that are positive and divide by the one that's negative. So that's 2x plus 1 times x minus 2 over x squared equals 0. Once I have a single log, then I can convert it to an exponential. Now this is natural log, which is base e, so that's e to the 0 power is equal to 2x plus 1 times x minus 2 over x squared. E to the 0 power is 1, and I have 2x plus 1 times x minus 2 over x squared. I can clear the denominator by multiplying by x squared on both sides. And I get x squared. I'll go ahead and multiply out that numerator. That's 2x squared minus 4x plus x minus 2. I can move all the terms to the same side, so I'm going to subtract x squared. And that gives 0 equals x squared minus 4. Oops, I can combine those two together. Negative 4x plus x is a negative 3x minus 2. And I can solve this quadratic by the quadratic formula. I don't think factoring will work on this one. I'm going to let a equal 1, b equal negative 3, and c equals negative 2. So that will give me x equals negative 3 plus or minus the square root of negative 3 squared minus 4 times 1 times negative 2 all over 2 times 1. This gives 3 plus or minus the square root. Negative 3 squared is 9. And 4 times 2, that would give me an 8, a plus 8 over 2. And this is 3 plus or minus square root of 17 over 2. And so I've got those two solutions, but with log equations, you need to check. So let's see the original equation. In the original equation, I'm taking a look at each one of these logs. I think the easiest one to look at is the log of x. And let me grab my calculator. All right, I got my calculator pulled up, and I want to type in my calculator 3 plus square root of 17. All right, let's try that again. Parentheses, 3 plus square root of 17 divided by 2. All right, so this gives me about 3.5. And when I look at my logs, this first one, 2 times a positive number will be positive, plus a positive will still be positive. And this next one, 3.5 minus 2 will be positive, and this is just an x, so log of 3.5 is also positive. So this solution is good. Now the other one will be 3 minus square root of 17 over 2. And this gives a negative number. So when I substitute this into x, that would be log of a negative, and I'll have to exclude that number. So my only solution will be x equals 3 plus square root of 17 over 2. So I showed you this example with the method of converting, but I want to show you that you can also do this with the property of equality. So just as a reminder, the property of equality requires us to have a log on the left and a log on the right. So let's rewrite my equation. Natural log of 2x plus 1 plus natural log of x minus 2 minus 2 natural log x equals 0. So I notice that this log is negative, so what I'm going to do is move it to the other side of the equation. That gives natural log of 2x plus 1 plus natural log of x minus 2 equals 2 natural log of x. I need to condense on the left, and both of these logs are positive, so I'm going to condense with the product rule. So since these logs are added, I'm going to multiply the logs together. That's 2x plus 1 times x minus 2. And on the right-hand side, I'm using the power rule for logarithms. I'm going to move that 2 into the exponent. So that gives natural log x squared. So now I have a log with the same base on both sides of the equation. So I can do the property of equality, which says what's inside the log on the left is equal to what's inside the log on the right. And when I get to this spot in the equation, I can multiply this out, and that would be 2x squared minus 4x plus x minus 2 equals x squared. I can move all the terms to the same side and combine like terms, and I get x squared minus 3x minus 2 equals 0. So you'll notice that this is the exact same equation that I got earlier. So then I could once again use the quadratic formula. I would once again get 3 plus or minus square root of 17 over 2. And I would have to check, and when I check, I would find out that only 3 plus square root of 17 over 2 is in the domain of our expressions. So either way, we could use the method of converting or use the property of equality to solve this logarithmic equation. We want to solve the logarithmic equation log base 3 of x plus 4 plus log base 3 of x minus 4 equals 2. On this question, I notice that I have logs only on one side of the equation. So I'm going to use the method of converting to solve this log equation. So in the method of converting, we start off with a log equation, y equals log base b of x, and we convert that to an exponential. That gives b to the y equals x. That conversion that we do is part of the definition of what a log is. In order for us to do that conversion, we need to have a single log on one side of the equation. We have the sum of two logs on the left, so we're going to use one of our condensing properties, which is called the product rule. The product rule says that if we have log base b of m plus log base b of n, we can condense that to a single log base b of m times n. So hopefully you see where this gets its name. It's the product rule because we multiply the m and the n together. So in this example, we have the sum of two logs with the same base. So we're going to be able to use that product rule for logs and write this as log base 3 of x plus 4 times x minus 4 equals 2. Once we condense it down to a single log, we can convert it to an exponential equation. That would be 3 squared equals x plus 4 times x minus 4. 3 squared is 9. I'll multiply this out to get x squared minus 4x plus 4x minus 16. You can combine like terms to get x squared minus 16 on the right hand side because the negative 4x and the positive 4x cancel each other out. And I'll solve this by isolating the x. I'll add 16 to both sides. So 25 equals x squared. Get rid of the square by square rooting both sides. And that gives x equals plus and minus 5. Square root of 25 is 5. With every log equation we need to check. So we're going to check x equals 5. It's log base 3 of 5 plus 4 plus log base 3 of 5 minus 4 equals 2. So I'm checking 5 plus 4 is a positive 9. 5 minus 4 is a positive 1. So we're going to be able to keep that because the log of positive values are defined. Then let's check x equals negative 5. It's log base 3 of negative 5 plus 4 plus log base 3 of negative 5 minus 4. I apologize, this doesn't equal 0, it equals 2. And negative 5 minus, that's negative 5 plus 4, that's a negative. Negative 5 minus 4, that's a negative. And log of a negative is undefined. So we have to throw that solution away. So the only solution to this log equation is x equals 5. We want to solve the logarithmic equation log base 7 of x plus 10 plus log base 7 of x plus 52 equals 3. So on this example, I notice that I have log only on one side of the equation. So I'm going to use the method of converting of y equals log base b of x. So that's our log equation. And we're going to write that as an exponential. B to the y equals x. Before we're able to do that conversion, I notice that I have multiple logs being added together. So I'm going to use the product rule for logarithms. The product rule looks like this. If you have log base b of m plus log base b of n, you can condense those logs into a single log, log base b of m times n. So we'll start by condensing, and that would give log base 7 of x plus 10 times x plus 52 equals 3. So we condensed on the left-hand side. And now that we have a single log, we can convert that to an exponential. So we'll use that base of 7. The log always equals the exponent, which is 3. And this expression equals x plus 10 times x plus 52. So let's work this out. Let's see what 7 to the third power is. That's 343. Let's multiply this out and we get x squared plus 52x plus 10x plus 520. I'm going to combine like terms and also move all the terms to the same side. And that gives 0 equals x squared plus 62x. And let's see, 520 minus 343 gives 177. Let's see if I can factor this. I don't know the factors of 177 very well. That's 1 times 177. It's not even, so 2 doesn't go into it. Okay, 3 goes into it. 3 times 59. All right, 3 times 59 will give me 177, and 3 plus 59 will give me 62. So I'm going to be able to factor this into x times x is x squared, and 3 times 59, and both of them have pluses. So we'll set each one of those factors equal to 0. X plus 3 equals 0. X plus 59 equals 0. And we get x equals negative 3 and x equals negative 59. Then I need to check both of these to make sure that they're in the domain. So let's check x equals 3. That's log base 7 of 3 plus 10 plus log base 7 of 3 plus, excuse me, that's a negative 3. So negative 3 plus 10 and negative 3 plus 52. And negative 3 plus 10 would give me a positive 7. And negative 3 plus 52 would give me a positive 49. And so I'm going to be able to keep that solution since it's in the domain of the log. And then I'll check the other solution. Let's check x equals negative 59. Log base 7 of negative 59 plus 10, that's a negative. And log base 7 of negative 59 plus 52, that's a negative. So log of a negative is undefined, so we're going to have to throw that solution away. So the only solution is x equals negative 3. We want to solve the logarithmic equation. I have log base 6 of 6x plus 1 minus log base 6 of x minus 6 equals 2. I do notice that I have log only on one side of the equation. So I'm going to use the method of converting to solve this log equation. That would give log y equals log base b of x, and be converted to an exponential by doing b to the y equals x. I also notice that I have multiple logs, so I'm going to need to condense them, and I see this subtraction here, so this time I'm going to condense with the quotient rule. The quotient rule looks like this. If you have log base b of m minus log base b of n, you would condense to a single log by using division or a quotient. That's log base b of m over n. So using the quotient rule, we would condense this to be log base 6 of 6x plus 1 over x minus 6 equals 2. And now that I have a single log on the left, I can convert this to an exponential. I'm going to use the base of 6. The exponent is 2. And this equals what's inside the log, 6x plus 1 over x minus 6. So 6 squared is 36. And that equals 6x plus 1 over x minus 6. I'm going to clear the denominator by multiplying both sides by x minus 6. So that would give 36x minus 216. On the right-hand side, the x minus 6 cancels, and I have 6x plus 1. I'll combine like terms, so I'm going to subtract 6x on both sides. That would give 30x equals, minus 216 equals 1. I would add 216 to both sides. That gives 30x equals 217. And I'll divide both sides by 30. So that gives x equals 217 divided by 30. So 217 divided by 30 is going to be about 7.2. So if I substitute a 7.2 into here, 6 times 7 is a positive, plus 1 is a positive, and then 7 minus 6 would be a positive, so I'm going to be able to keep this solution of 217 over 30. I want to solve this logarithmic equation, which is log base 5 of x plus 2 equals log base 5 of 4x minus 5. And this time I can see that I have a log base 5 on both sides. This is an indication that we're going to use a property called the property of equality, or other sources call it the one-to-one property. So this is what it looks like. When you have log base b of m equals log base b of n, so a log with the same base on both sides, you can simplify your equation saying that what's inside the log on the left is equal what's inside the log on the right. So that's what we're going to do in this example. We have log base 5 on both sides. So what's inside the log on the left, x plus 2, will equal what's inside the log on the right, 4x minus 5. And we're going to solve the equation that's left. I'm going to get all the x's together, so I'm subtracting x on both sides. And that gives 2 equals 3x minus 5. I'm going to add 5 to both sides, and that gives 3x equals 7. And I'll divide both sides by 3. I get a solution of x equals 7 over 3. We do need to check that. 7 over 3 is, let's see, about 2.3. So if I put a 2.3 in for this x right here, 2.3 plus 2, that's going to give me a positive. And if I put a 2 in right here, 4 times 2 will be about 8, minus 5, that will be a positive. So 2.3 or 7 over 3 is in the domain of this logarithmic expression, so we're going to be able to keep that solution. We want to solve this logarithmic equation. We have log base 3 of x squared minus 36 equals log base 3 of 5x. So with logs on both sides of the equation, we're going to use the property of equality. The property of equality says that if we have log base b of m equals log base b of n, that's log with the same base on both sides, that we can say that's what is inside the logs is also equal. So that allows us to simplify this equation to be x squared minus 36 equals 5x. Now this is a quadratic equation. I'll move all the terms to the same side to give the equation x squared minus 5x minus 36 equals 0. And I'll try to factor. So that would give x times x is x squared. And I want two numbers that multiply to be 36. I'm thinking of the factors of 36, 1 and 36, 2 and 18, 3 and 12, 4 times 9, and 6 times 6. And I notice that 4 times 9 has a difference of 5, which is my middle number. So I'm going to use the 4 and the 9. The 4 and 9, and I need the negative 5, so I put a negative on the bigger number. And I'm going to set each factor equal to 0. I got it factored to be x plus 4 times x minus 9. And I use the zero product property to set each factor equal to 0. And that gives x equals negative 4 and x equals 9. I need to check both of these. I'll check x equals negative 4. That will give log base 3 of negative 4 squared minus 36 equals log base 3 of 5 times negative 4. So I can see right here 5 times negative 4 is a negative, so I'll have to throw that solution away. On the left-hand side, 4 squared, negative 4 squared is 16, and 16 minus 36 would also give a negative here. So let's check the other one. We're going to check x equals 9. That gives log base 3 of 9 squared minus 36 equals log base 3 of 5 times 9. 5 times 9 is positive. 9 squared is 81. 81 minus 36 will also be a positive, so I'll be able to keep that 9, and 9 is the only solution to this logarithmic equation. In this one, we want to solve the logarithmic equation 2 log base 4 of 7 minus x minus log base 4 of 2 equals log base 4 of 18. I have logs on both sides of the equation, so I'm going to be able to use the property of equality. But in order to use that property, I need a single log on both sides. So I'm going to use some other properties to condense the expression first. I'm going to use the power rule for logarithms to move this power to the exponent, or move this coefficient to the exponent. That would give log base 4 of 7 minus x squared minus log base 4 of 2 equals log base 4 of 18. And now I need to condense these two logs together. Because we have a minus here, we'll use the quotient rule to condense. And that would give log base 4 of 7 minus x squared over 2. And I'm just copying down the right-hand side. And at this point, I can use the property of equality because I have log base 4 on both sides. And what's inside those logs need to equal each other. So 7 minus x squared over 2 will equal log, no log. What's inside the log is 18, so it'll equal 18. And I'm going to be able to solve this. I'm going to multiply both sides by 2, and that gives 7 minus x squared equals 36. We can get rid of that square by square rooting both sides. And that gives 7 minus x equals plus and minus square root of 36 is 6. And now I'll get x by itself, so I'll subtract 7. And that gives me negative x equals negative 7 plus and minus 6. I'll divide by a negative 1, and that would give me x equals negative 7 minus and plus 6. Negative 7 minus 6 is negative 13. Negative 7 plus 6 is negative 1. So those are my two potential solutions. And let's check each one of them. Let's check x equals negative 13. 2 times log base 4 of 7 minus negative 13 minus log base 4 of 2 equals log base 4 of 18. And because this is minus and negative, we change that to plus. That's 7 plus 13. And so I'm going to be able to keep that solution of negative 13. And then if I check x equals negative 1, the same thing happens. I have 2 times the log base 4 of 7 minus a negative 1. And that minus a negative 1 changes to plus, so that's a positive 8. So I'm going to be able to keep that solution of negative 1 as well. Okay, so I did make a mistake here, so let me go back and make a correction. When I divided by the negative 1, I should have changed this 7 to the opposite sign. I changed these to the opposite, but I forgot to change the other one. So let's correct that. So this should be a positive 7. So both of these should be positive. So I have 7 minus 6, and that would give a 1. And 7 plus 6, that would give a 13. So I really need to check a positive 1 and a positive 13. So let's go back and check that. So I'm only changing this part in the inside. So that would be 7 minus 1, and that's a positive. So I'll be able to keep that solution. And 7 minus 13, that would give a negative. So I'll have to throw this solution away. So the only solution would be x equals 1.
Thank you for checking out my videos. Have a great day.